In this video, I want to find antiderivatives for several common functions. The goal here is to have many antiderivatives that we can recognize on sight so that we can use them in other calculations and even in applications. So I'd like to fill in this table. The left-hand column gives us a function. Some of the functions involve a constant k. Anytime you see a k, it's just some constant. In the right-hand column, we're going to find the most general antiderivative. So we start off with x to the n. So one of the ways you can always find a rule, and just good advice for doing mathematics in general, is that if a general case like x to the n doesn't make sense to you, then maybe doing some specific examples will help. So let's find an antiderivative for x squared. Well, that would need to be an x cubed, but to make it actually the antiderivative, make the derivative of this actually be this, I need a 1/3 in there, right? Because 3 times 1/3 is 1, and then x squared, of course, plus c. And then maybe we try an x to the third, right? And very quickly we'd see we'd need a 1/4 out front and x to the fourth, and I just keep going in this fashion. And what it seems like is I always have a new exponent, and then I have to divide by that new exponent. And in fact, I even see what that new exponent is. I started with 4, I added 1 to get 5, and then I had to divide by that new exponent. So in general, what I think is going on is I have to add 1 to the exponent, and then divide by that new exponent. All right, well, we can imagine taking a derivative. I'd have to multiply that down. N plus 1 over n plus 1 would give me 1. Take 1 away from the exponent and have x to the n. But let's make sure that this didn't just work for whole numbers. So let's imagine I have the square root of x, and we all know the square root of x is x to the 1/2. Add 1 to that, and I'll get 3/2. Dividing by 3/2 is the same as multiplying by 2/3. Multiply the exponent down to take a derivative. 2/3 times 3/2 is 1. 3/2 minus 1 is 1/2, and that even worked for a fractional power. And so I can write a rule that this most general antiderivative is 1 over n plus 1 times x to the n plus 1 plus some arbitrary constant c. All right, moving on, I need to find an antiderivative for the sine of k times x. Well, another good little problem-solving strategy in a math class is if there's something in your way or something seems complicated, make the problem just a little bit easier. So maybe someone just gives me the function sine of x. And we say, well, the antiderivative is going to involve cosine. But if I take the derivative of cosine, I actually get minus sine, so we can fix that just by putting a minus out front. All right, well, the problem actually on my board is sine of k times x. So maybe I try minus cosine of kx. But if I took this derivative, I would get sine of kx times k because of the chain rule. Well, if I put a 1 over k out front, that'll take care of that, plus an arbitrary constant c. So my most general antiderivative for sine of kx is minus 1 over k cosine of kx plus c. Looking at a rule for cosine, I have a feeling you could actually guess it based on what we just did. So pause the video and see if you can fill in this blank, even if you have to jot down a few thoughts. Okay, the most general antiderivative is 1 over k sine of kx plus c. Really thinking of that 1 over k is undoing what the chain rule would do if I had that kx in there, so just an x. All right, I need a function whose derivative is secant squared. Well, of course, that's going to be a tangent of kx plus c, but the chain rule would multiply by k, so I'll have to undo that. For the same reason, I can go on and write down the most general antiderivative of cosecant squared. Looking in this next spot, I need a function whose derivative is secant times tangent. Of course, that would be secant plus c. But again, if I take this derivative, I'd end up with a times k, so I have to undo that. And again, the same reasoning we've been using here will help me out with this spot. I need a function whose derivative is e to the kx. Well, that would be e to the kx, but I'd have to divide by k because of the chain rule. All right, I need a function whose derivative is a to the kx. So let's think a little bit about that. I think it'd be natural to maybe guess that the answer should be a to the kx maybe times 1 over k. But then I remember something about the rule of taking the derivative of an exponential function whose base is not e. And if I take this derivative, I'd get the 1 over k times a to the kx times k because of the chain rule, but also times the natural log of a from the rule itself. Well, those would cancel. The 1 over k and the k would cancel, but I still have that natural log of a, and I didn't want it. So what I realize is I also have to divide by the natural log of a. And there is my most general antiderivative. All right, in these three spots, I have three more functions. They should look like the derivative of something, right? They should remind you of a derivative rule, right? That's really what's going on here. We're saying, hey, what kind of function has this as a derivative? Why don't you pause the video and see if you can think up functions that would have these derivatives, and then try to think about the chain rule and put a 1 over k in a good spot to kind of undo it. All right, so I need a function with a derivative that is in the format of a 1 over the square root of 1 minus k squared x squared. Well, again, maybe that k is getting in the way, the arbitrary constant. Maybe you'd have a better luck, maybe you'd have better luck at recognizing a derivative formula if I just let k equal 1, and I had 1 over root 1 minus x squared. And I'd bet, even if you had been having trouble thinking about this one, now you'd say, hey, I recognize that. That's the derivative of inverse sine. Well, replacing x with x squared gives me this, which means my formula would need a kx in it and a 1 over k. 1 over k sine inverse of kx plus c. That gives you two more spots in this table to fill in, and I think I'm going to let you do those two as an exercise because I've simply recreated a table here that's on page 283 of your textbook. So give yourself a chance to try to fill in these two blanks, and then check your work on page 283.